Okay, 11 a.m. and we can continue. So the next week is going to be a very short week. So we're going to have only 2 days of classes, right? Monday and then Tuesday. So we're going to have only 1 lecture. So most likely, next week I will finish this chapter about Lagrangian formalism, right? So it's time for me to start to post the next homework about Lagrangian formalism. And as we discussed in the previous lecture, most likely after that, after this homework, there will be the second midterm exam. Again, as I said, it's usually very close to the final exam. There are like a couple of weeks gap between 2 exams. Okay, anyway, so back to the Lagrangian formalism examples, right? So you remember we started discussing this example, but we haven't finished. So a few words about the system. Okay, I prepared it since we covered it in the previous lecture. So we have a cylindrical surface, right? And there is a mass. It's just a point mass m is confined to move on the surface under the influence of sort of 3-dimensional Hooke's law, right? Basically like a spring force, 3-dimensional spring force. And the origin of that, and the origin is over here, that a point where the force equals to 0, right? So, all right, as a result, because of that force, mass m is confined to move on the surface, and of course, no friction, because the friction will change the form of the Lagrange equation, right? So in this semester, we're not going to deal with friction forces in our systems. Every time the systems are going to be frictionless, right? So that's what we have here. Mass slides on the surface without friction. Okay, then, so we have one mass in 3-dimensional space. So without constraints, you need 3 coordinates, which would be linearly independent. But in this case, we have one constraints the surface of the cylinder. In cylindrical coordinates, rho equals to r capital. In this case, so we have one constraint. So as a result, it reduced, we discussed it, it reduced number of linearly independent coordinates to 2, which we call generalized coordinates. You remember in the previous lecture, we discussed that idea of generalized coordinates. So in this case, we decided to use z and phi as our generalized coordinates, right? So as a result, then we wrote down the Lagrangian. We did it. So now we need to write down Lagrange equations in order to get equations of motions, right? So now the next logical step. Probably first I will write for z Lagrange equation for z. So it will be d. The first symbol is immediately wrong. So partial derivative of the Lagrangian with respect to z equals to total time derivative out of partial derivative with this of L with respect to z dot, with respect to z dot. So Lagrange equation, again, form is exactly the same. So now, okay, guys, be careful, right? Because like, for example, in the next example, Lagrangian will be kind of long, right? Many terms. So carefully look at each term one by one to make sure that you don't lose any term when where there is a z, for example, or phi. It's a very common place when on the exam you're running, right, trying to move fast. As a result, you can lose a couple of terms, 1 or 2 terms, where there is a this or that variable. So be careful at this point. Very common place for mistakes. All right, so dl over dz. So no z again. You remember in the Lagrangian formalism, we treat q in general, q and q dot as independent variables, basically, right? So in this case, so at this point, so z and z dot has nothing to do with each other. So we treat them as independent. So it means here we don't have z. We're trying to find all terms where there is z. This is no z. Here we have z dot. Then again, no z. Actually, constant. Okay, look, guys. If a Lagrangian has a free constant, it means what? What can we do with that constant? We can trash it immediately. Why? Because look at the structure of the Lagrange equation. Every time you have to differentiate L, and again differentiate Lagrangian. So every time that constant would disappear anyway. So in this case, for example, this kr squared over 2, I could have trashed it, right? And the equation, it wouldn't affect the equation of motion. Lagrange equation is equation of motion. So I could have trashed it, and I would have just minus kz squared over 2. Right? So constant in the Lagrangian are not important. Okay, so now, anyway, back to our equation. So so z is only here, so it will be minus kz, because z over 2, 2 will appear, will be cancelled with that 2, so it will be minus kz. So left-hand side, and now it must be equal to d over dt and dl over dz dot. Z dot only here. Right? Again, this z has nothing to do with z dot. So z dot here, so we'll have mz dot. And then we differentiate one more time with respect to time, total derivative. So we're going to get mz double dot. M stays constant, of course. So it will be mz double dot. So that's our second order differential equation, right? Which we need to solve. Of course, we can rewrite it slightly. So we will get z double dot equals to minus k over m z. And of course, we can introduce so we can introduce omega, right? And we can write it as minus omega squared z, right? So simple harmonic motion. We know the solution of this, right? We spent the whole chapter 5 discussing all possible solutions of equations like this. So as a result, we get z as a function of time equals, I'm going to use phase-shifted cosine solution, probably the most convenient form of that solution. A cosine omega t minus, I think I use delta, it doesn't matter, yeah, I think delta. Right. So that's first part of the solution. So it describes what system particle do in the z direction, and actually in z direction it oscillates around, of course, the origin, right? Around the origin. So it's going to oscillate. So now let's see what happens in the phi direction. So, okay, let me put the first bullet, second bullet. So now it's a dl over d phi equals to the total derivative with respect to t out of partial derivative with respect to phi dot. Again, you see, it doesn't matter which coordinate you use, the form of the Lagrange equation stays the same, which is one of the major advantages of using Lagrangian formalism. Okay, now, what's the value of dl over d phi? No phi, again, phi dot and phi, nothing, they have nothing to do with each other. Again, no phi, no phi, no phi. So when, in the cases like this, so when, if a certain variable is missing from the Lagrangian, it's not explicitly present, right? Like in this case, phi, that variable is called ignorable or cyclic. I know some people pronounce it cyclic, but whenever I see cyclic, it sounds like sick, right? So I don't like it. So I usually pronounce cyclic, right? But you can use whatever you want. You can pronounce it any way you want. So so again, if a certain coordinate is missing, and again, it's we're talking about q's, not q dots, right? If in this case, like in this case, phi is missing, that in this case phi is ignorable or cyclic. And immediately, you will see, generalized momentum is conserved. But we will see it immediately. It follows from the Lagrange equation. So let me write first what I just said. yeah, we'll write underneath. Since phi is missing in L, phi is called cyclic or ignorable. Cyclic or ignorable. It's a very common term. Right. So cyclic or ignorable. Let me underline it. Yeah. So in this case, as a result, immediately, you remember what is this? It's a generalized force, right? In case, since phi is the angle, so this is torque. Then this dl over d phi dot, you remember the previous class? This is generalized momentum. And in case when phi is the angle, it's a angular momentum, right? In this case, this was generalized force. And in the case, since z is a translational coordinate, that is actual force. And this is generalized momentum. But again, since z is a translational coordinate, this is just linear momentum. Again, linear momentum, here angular momentum. This is force. In this case, it's a torque, right? You remember the previous class, previous lecture. Okay, so now as a result, this is 0. Nice. And immediately, first integration is done. Integration over t, we do it. It's done basically for us automatically. So as a result, immediately, dl over d phi dot equals constant. So conservation of, in this case, conservation of angular momentum. So generalized momentum is conserved. Right. And of course, now when we write it down explicitly, of course, you will see that that is angular momentum. Okay, so now let me write underneath. So dl over d phi dot. A constant, did I label it somehow? No. Yeah, I did. Right, so dl over d phi dot. Phi dot is only here. So it will be m r squared phi dot. M r squared phi dot. So, so it's a m r squared phi dot equals to a constant, this constant, right? And let me call it L sub z, because that's the angular momentum in a z direction, right? So L sub z. So, and yeah, that's what, in this case, generalized momentum is an angular momentum, and it's conserved. So, as I said, so now, if you have a Lagrangian, and you see immediately that one of the generalized coordinates is missing, for example, Q5, right? So it means that the corresponding generalized momentum, like in this case angular momentum, in this case linear momentum, generalized momentum is conserved. Immediately you can say that. So finding which quantity is conserved, it's very easy once you have Lagrangian. All right, so let me again, all right, so it's angular momentum. Okay, and of course, since mr squared a constant, so we can write that phi dot is constant. So we have a constant angular velocity. So the particle also basically spinning around z-axis with a constant angular velocity. So as a result, we have superposition of two motions. First, z up and down oscillates, right? Where is it? Here. And circular motion on the surface with constant angular velocity. So we have uniform circular motion, oscillations in z direction, and uniform circular motion. So as a result, we're going to get a motion. All right, you know what? I thought about drawing it over there, but it would be too much. So let me quickly draw a different picture, all right, in order to describe, in order to show the motion. All right, so that's our cylinder, and that's the origin, right? And motion will be, okay, let me draw also this line. All right, so motion will be like this. So Something like this. Non-stop circling and oscillating up and down. Of course, around this xy plane. Right, xy plane. So, it's done. Right? So we know everything about this particle, about the motion of this particle. Right? So I'm just checking if I mentioned everything. Mm-hmm. Yeah. So now let's look at the next example. So pretty much now this class, and then probably half of the next class, it will be all about examples. And these examples, they're kind of lengthy, not completely trivial. And actually, most of the problems about Lagrangian formalism, they're reasonably lengthy. Straightforward, because most of the time it's all about calculus. Physics and thinking only at the very beginning when you're trying to write down the Lagrangian. Once Lagrangian is written, the rest is just calculus, boring calculus, right? And then interpretation of the results at the end. So next example. And you know what? Strictly speaking, I think applying Lagrangian formalism is easier than Newtonian formalism, right? Kind of more structured, less options, right? Easier. And I remember when we had to take qualifier exam, and when on the written part, I remember when we saw on the classical mechanics that they offered, for whatever reasons, 2 problems about the Lagrangian formalism. We were excited, right? We were ecstatic. Yeah, we can make mistakes, silly mistakes here and there, but overall the problem will be there. It's again, as I said, because it's well structured. Right? Much easier to work with Lagrangian formalism than with Newtonian. All right. So the system is like this. We have a wedge. Which way oriented? Okay, this way. Okay, I'm just trying to estimate the amount of space that I might need. So let's see. We have a wedge. Right. Okay, good enough. Then this wedge is on the horizontal surface. Again, no friction. Friction will ruin the game. Okay, not ruin, change it significantly. So no friction. So this wedge of mass m capital, angle of inclination is given alpha. And then the length of the inclined plane is also given. Okay, let me start writing what is given. So we have, okay, let me also add on top. And now there is a box on top. Oh. Box. Right, so of mass m small. Again, it slides. Okay, it moves. I don't know if it slides down or up, right? Okay, of course it slides down, right? In this case, right? Because this box M basically is released from the top, right? Released. So of course it will slide down, and this wedge will be sliding that way. And again, no friction. So now let me write down what is given. So M small, M capital, then angle of inclination alpha, and then the length of the inclined plane is given. And again, as I said, no friction. Right. So that's the situation. Let me check if that's all what is given. Yeah. So the problem asks, find a travel time of this box from the top. Yeah, another condition, it was released. It was released, so I can write, so V naught equals to 0. V sub 0 equals to 0. Initial condition is given. Right. And so, yeah, we need to find the travel time. Let me write so. Find T, which way I label it? I think TL sub L. Yeah. Let's find TL, the travel time. Why TL? Because, yeah, it's the time that box is needed to cover the distance L, the length of the incline. Again, yeah, this problem can be solved using a Newtonian formalism, but you know there are so many forces in all possible directions, so it's a not very pleasant experience, right? Using Lagrangian is easier, again, because you have to deal with energies easier. You don't have to suffer with directions, right? Okay, so first of all, before we start writing down the Lagrangian, we need to first, again, as usual, choose a coordinate system, basically a reference frame. And again, you remember, it must be inertial. Actually, on my oral qualifier exam, I have a problem like this. All right. And I remember one of the first questions I was asked, so can we position, for example, the coordinate system, the origin, the reference frame, for example, on this wedge? Because you remember, usually in physics 1, when we have just an inclined plane, which doesn't move, right? And of course, every time we would position coordinate system on here at the top of this wedge, right, with x-axis along the inclined plane. But in this case, we cannot do that, right? Because the wedge is moving, and that is, of course, accelerating, not just moving. So this is a non-inertial, would be a non-inertial reference frame, right? So we cannot position our reference frame on any of these objects. So we need to ground it somewhere outside, right? So I'm going to ground it somewhere at some distance from the wedge. Some sort of general situation at arbitrary moment of time t when they are slightly away from, somewhat away from the origin of the reference frame. So let me choose it this way. So this is x, and I will stick my y-axis into the ground. So it's grounded. And again, I will emphasize it's inertial. Okay, let me write it. Because if you pick a non-inertial reference frame, you cannot use Lagrangian formalism, period. Right. Although sometimes I can see on the qualified students try to use a non-inertial reference frame. It's a big mistake. Right. Okay, so coordinate system, and now let's try to understand how many generalized coordinates are needed, because obviously we have constraints. Two objects, some constraints are imposed on both of these objects, right? So, so without constraints, we would need, of course, 4 coordinates, and they would be linearly independent, right? So without constraints, we would need something like, okay, let me first introduce those generalized coordinates defining position of both of these masses, and then I will start using them. So this is, let me use x small, and of course, coordinate of the box. And this will be y small. Then wedge. This is basically point mass. The wedge. Wedge is this rigid object, right? It doesn't matter which point you're going to use to define position of the wedge. You can use this point. You can use this point. You can use center of mass if you want to suffer more, right? Finding that point. Right? I picked this point, the top of the wedge. I'm going to use that point to define position of the wedge. And then if you know position of that point, you can find position of any point of the wedge. It's a rigid object, right? Because you understand me, right? So I will use this point. So as a result, this will be x capital, and y capital will be 0, of course. Y capital, right? So this is the point which I'm going to use to define position of the wedge. Right? Of course, y capital is 0. Maybe I should write immediately. So it's a 0. Okay, so let me write. So two objects in 2D space. So of course we need 4 coordinates, which are x small, y small, x capital, y capital, if we don't have constraints. But so now we have 2 constraints. Which are those? Very often, okay, not very often, all the time I'm trying to identify those constraints, right? So first, for the wedge, it moves on the horizontal surface. So there is a force of constraint, normal force. But of course, we don't care about forces. We just usually constraints. And we used them to write down transformation equations, which we are going to do, which we are going to write. So, okay, let me write that. Which way I stated it? Okay, the flat surface for M, 2 constraints. So first, flat surface for M capital, and then the second inclined surface for M small, right? So, and then so as a result, we have 4 coordinates we need without constraints, plus we have, okay, minus 2 constraints. As a result, we need 2 generalized coordinates, right? So 4 minus 2, so we need 2 generalized coordinates. And now at this point, yeah, we need to pick. You can pick any generalized coordinates you want, which you think is more convenient for you, right? I think for 1 coordinate should be used to define position of the wedge. I think it's more or less obvious, right? And 1 coordinate to define generalized coordinate, to define position of the box, right? I think for the wedge, the choice is obvious, right? So we just need to introduce coordinate which will define position of that point relative to the origin. I will introduce this. Right. So this will be Q2. It's the second generalized coordinates. Okay, slightly out of order. Who cares, right? You could have labeled it Q1, but I decided to use Q2. Because the major point is M small, and the secondary, at least I treat it, and the secondary object is M capital, right? So now about the second generalized coordinate. I think it's more or less, again, obvious, so that the second coordinate should be defined position of the block on position along the inclined plane. Some people pick the second coordinate measuring from this point, right? But you will see when we start writing transformation equations, right? This is not the best option, because in that case, in order to write transformation equations nicely, you will have to introduce the length of the wedge, but it's not given, so it's just additional constant. It is not going to change much. It just you will have to add additional constants to the problem. Why? So in order to avoid dealing with that, let me introduce the second generalized coordinates, which is measured from the top of the wedge to the current position of the block. So that's our Q1. Q1. In that case, when we start writing transformation equations, everything matches nicely, right? And I think this is the most convenient. Right. Or again, if you would define, if for example you decide to define position of the wedge using this point, in that case Q2 will be from this point to this. and Q1 will be would be from this point to the current position of the block, right? Again, choice of generalized coordinates are not unique. You can come up with any generalized coordinates. Some of them will be more convenient, some of them less convenient, right? Okay, I picked these guys. Right, so now I can state, so we have Q1 and Q2. Then another thing, you remember I said that coordinate system, everything must be written relative to inertial reference frame, right? In original coordinate, Lagrangian, which I'm going to write using Cartesian coordinates, using this xy and xy, must be written relative to inertial reference frame. And then your generalized coordinates can be attached to anything. Like in this case, you see Q1 measured position of this block relative to some point which is accelerating. So what a big deal, because our original Lagrangian, which I'm going to write, is written relative to inertial reference frame. All these xy measured position of the objects relative to inertial reference frame. Right? So what is inside of those x's and y's, right? Who cares? So those generalized coordinates can be attached to anything. Anything which can be stationary, can be accelerating, can be screaming, can be doing whatever stuff it wants to do, right? We don't care, because our Lagrangian will be written anyway relative to inertial reference frame. Right? So no any troubles. So next, I think now it's time to let me write Lagrangian again first using linearly dependent coordinates, and then I will write transformation equations and rewrite Lagrangian in terms of generalized coordinates. Right? Okay, so let me check if I mentioned everything which I was planning to mention. Yeah, it looks like. Yeah. Okay, if I recall, I will fix it. So I will put a bullet, and again, Lagrangian equals T minus U. And now I realized that because I will have to write down potential energy, I need to make a decision about the reference level, right, for my potential energy. I decided to use this as a reference level. Of course, the origin, the level of the origin. So this will be my U equals 0. So the potential energy of the mass, M, will be negative, right? Because it's below the reference level. Right. So, okay. Probably first I will write which, M small, M capital. Yeah, let's start with M capital, easier to write. So M capital, M over 2, and then X capital dot squared plus Y capital dot squared. So kinetic energy of the first mass. Again, you see right now I'm writing down Lagrangian in terms of linearly dependent coordinates. We will reduce it, we will change it. Then plus M small over 2 X small squared plus Y. I mean, X dot squared plus Y dot squared. And potential energy, of course, minus, because that's how we introduce Lagrangian. And potential energy, of course, will be minus, potential energy is negative, mg and y, right? Because this distance is y. So minus mg y. And again, guys, you're going to do homework, plenty of problems, right? A very common place for mistakes. Students don't define where the reference level is. As a result, they just write positive value, right? As a result, they're missing minuses, right? So be very careful at this point, right? Plenty of completely unnecessary mistakes over there. Define the reference level. And if an object above that level, potential energy is positive. If an object below that level, potential energy is negative. So Okay, so again, it's right now it's not the final form. So now we have to make a transition to generalized coordinates. So we need to write transformation equations. Now, transformation equations. So, which allows us to move from x small y small x capital Y capital to Q1, Q2. So this method is basically like a fail-proof method. If you follow this, first write in Cartesian coordinates, then transformation equations, then in generalized coordinates, and but of course at the end I will show you kind of easier way, but it can be tricky sometimes. Easier way of writing down the Lagrangian, but it's more higher chances of making mistakes. So transformation equations. So let's start with x capital. So x capital, how can we write it in terms of Q1, Q2? Obvious. X capital equals to Q2. So it's very simple. Then y capital. Obviously, y capital is just 0, so we don't need to write it in terms of Q1 and Q2. Then next, x small. You know what? I'm thinking, should I, in terms of space, Okay, let me write underneath. X small. So again, writing down transformation equations, pure geometry. Trivial, simple geometry. So x small, it's from this point to that point, so this distance. So it means that x small equals to Q2, right? You see this distance plus this small part, which is Q1, and this angle is also alpha. You see, this angle is also alpha. It's a plus Q1 times cosine of alpha. So Q2 plus Q1 times cosine alpha. Simple geometry, as I said. So it's a Q2 plus Q1 times, cosine of alpha. Transform. Let me check if I'm sure that's correct. Just checking still. Yeah, of course. So now y small. So y small, it's easier. So it will be just Q1 times sine alpha. This is just a simple geometry. Q1 times sine alpha. So these are our transformation equations. So what else do we need in order to start rewriting the Lagrangian? We need to take time derivatives. So let's prepare that here. So as a result, I can write, of course, x capital dot, it will be y2 dot. Of course, y dot equals 0. And then x dot small and y small dot. So it will be Q2 dot plus Q1 dot, and cosine of alpha. Alpha is a given constant. So now y dot, of course it will be Q1 dot times sine alpha. So now we are ready to start rewriting the Lagrangian. So just we need to grab this, plug that grab, also plug, and then after dealing with a little bit of mass, we will be able to write the final form of the Lagrangian written in terms of linearly independent coordinates. That's what we want to reach. The Lagrangian must be written in terms of linearly independent coordinates. Right, so now L equals m capital over 2. This is 0, this is y2 dot, of course squared. Right, to y2 dot squared. Wait, y2 q2, damn it. Q2 dot squared.
So okay. When we take derivative of x, does the cosine not get affected?
Oh. Cosine?
Yeah.
Cosine of a given constant. Alpha is a constant. It's not a variable.
Okay.
So we don't have to differentiate it. That's why when I was writing that down, I emphasized, guys, alpha is a given constant, right? So of course it's not a
Okay. I
variable.
must have missed.
We not change the angle of the incline. Okay, so the next, this kinetic energy of small m plus m over 2 and x dot squared. So we need to square this. Let me immediately square it. So it will be q2 dot squared plus q1 dot squared cosine squared alpha. All right, I'm just squaring x dot. And the coupling term plus 2 q1 dot q2 dot cosine alpha. All right, so I just squared x dot squared and now y dot squared. So here, just one term, it's easier. So plus q1 dot squared sine squared alpha. Actually, these curtains appeared here naturally, not for decoration. It's just because first, when I started, Sunip was helping me. So when we started switching to, started using the green screen effect for lecturing Physics 1 and Physics 2. So first I used those curtains. So just move them and use green screen effect. But this color is too bright, right? So as a result, it was difficult for software to handle that. There were lots of leakage. So as a result, I bought sort of professional green screen, all right, to use it. And this, they were just lazy to remove. As a result, now I have sort of like a decoration around the whiteboard. So back to our stuff. So that's kinetic energy, and now plus mgy, and y is over here. So plus m small, g, and y, it's q1 sine alpha. Okay, big mess. Now let's just simplify it slightly. Let me combine these two guys, these two terms, right? So it will be m capital plus m small divided by 2 times q2 dot squared. Right, so Lagrangian will be m capital plus m small over 2 times q2 dot squared. Okay, probably I should put a bracket. It looks a little bit not nice. Now, then this and that, of course, can be combined, right? So this and that, giving us q1 dot squared. So plus m over 2 q1 dot squared, and the coupling term, this plus 2 q1 dot q2 dot and cosine of alpha. That's it with the bracket. And the potential energy now with plus. Yeah. So plus m small g q1 and sine of alpha. Okay, so that's the final form, final form of the Lagrangian. I can frame it because, again, as I said, that's the most important. Once the Lagrangian is written, the rest is just boring calculus. You just differentiate first, then start integrating. So physics is over at this point. Actually, physics was over after you introduced generalized coordinates and wrote down the transformation equations with the first form of the Lagrangian. The rest is just pure calculus. And that's the beauty of the Lagrangian formalism, right? And again, all the forces of constraints basically here in the transformation equations. When you use that geometry, when you look at the picture, use geometry, then you don't care about the forces of constraints. Of course, use geometry where constraints are obviously visible. Right? You see how nice is that? Of course, it's kind of a little bit lengthy, bunch of terms, but again, they're all scalar functions, scalar quantities. All right, so what else I wanted to mention? Okay. This system, is it a coupled system? Obviously it is. Motion of one object depends on the motion of the other one. Right, so it's a coupled system. How does it reflect, how does it affect the Lagrangian? If your system is coupled, there must be a coupling term. It means that the term where inside of the term there are both Q1 and Q2. And we do have this. This is the coupling term. This term is responsible for describing the coupling in this system, right? And very often on the qualifier exam, oral, right, and written, mostly oral, if we give a system, coupled system like this, right? And very often students immediately jump and start writing down the Lagrangian kinetic energy and potential energy in terms of generalized coordinates. Of course, it's impossible. Okay, I've never seen students would succeed if they would jump and start writing down Lagrangian in terms of generalized coordinates, skipping these transformation equations, because all the time coupling term is missing. So you need to every time first write in Cartesian coordinates, then transformation equations, and then after a little bit of the math like this, coupling terms appears automatically. So far, I've never seen a student who would succeed writing down the Lagrangian. They can write this term, they can write that term, but coupling term all the time would be missing. Unless you're very, very experienced, solved a gazillion number of problems like this, maybe you can immediately write that coupling term. Right? So be careful, right? So use what is called the fail-proof approach, right? So this, and then the Lagrangian. Usually on the oral exam, once I see the transformation equations are correct, sometimes I just, okay, enough, right? So I can see that the rest is just algebra. We can stop and we can move to another question. But if system is not coupled, if there is no need in you know that there wouldn't be any coupling term, will not be any coupling terms, right? Yeah, then of course you can start writing the Lagrangian immediately. Basically like in this example, right? We have one object, right? So there is nothing to couple with. Okay, so now it's time to erase this, and so after this, just Lagrange equations. Another thing, you remember, okay, I should have probably mentioned that before I started erasing. You remember here I wrote down some words about coordinates which are cyclic or ignorable. If a certain coordinate is missing, it's not explicitly present in the Lagrangian, then we call that coordinate ignorable. Look at our Lagrangian. Which coordinate is missing? Again, if there is a q dot, again, it doesn't mean that coordinate is present. So yeah, which coordinate is missing? Q1 is there, so it's not ignorable. And of course, as a result, the corresponding generalized momentum is not going to be conserved. But Q2, you see, we have Q dot, Q2 dot, Q2 dot. But again, Q2 and Q and Q dots, we treat them as linearly independent. They have nothing to do with each other. So Q2 is missing. It's not explicitly present in the Lagrangian. So it means that that coordinate is ignorable or cyclic, and the corresponding generalized coordinate, generalized momentum is going to be constant, is going to be conserved. Again, what is that? Of course, we will see. Okay, so now Lagrange equations. Probably first I will write for what? For Q2, I think. Yeah, let's start with Q2. All right, so partial derivative of a Lagrangian with respect to Q2 equals to the total derivative with respect to time out of partial derivative with respect to Q2 dot. Again, you see the form of the Lagrange equations all the time the same. dl over dq dot, as we just discussed, Q2 is ignorable. Let me write underneath, probably over here to save time, to save space over there. So Q2 is cyclic or ignorable. It's a very common term, right? Used a lot because lots of systems where something is conserved. After all these examples, probably on Tuesday, right, I will sort of make a short summary about all these laws of conservation, right, or conservation of energy, how it changes the Lagrangian, then conservation of linear momentum, and then conservation of angular momentum. Right? So we will discuss that. So cyclic and ignorable as a result immediately. So this dl over dq2 is 0. Nice, right? And as a result immediately, dl over dq2 dot is constant. All right, so as a result, partial derivative of L with respect to Q dot, which is, again, generalized momentum, equals to constant. So now let's write down explicitly that derivative with respect to Q dot. Again, careful. You see, bunch of terms, so careful. One at a time. Slowly move from left to right to make sure that you don't miss any term where this or that variable is present. Right? Because, again, very common place for silly mistakes. All right. So Q2 dot, this, right? Then here and nowhere else. So 2 will be canceled, that 2 with this, so we'll have m capital plus m small Q2 dot, Q2 dot. And then this, again, these 2 and these 2 will go, so we'll have m Q1 dot plus m Q1 dot, right? And cosine of alpha equals to constant. What is that? It's a conservation of linear momentum in the x direction, right? So because Q2 basically defines position, defines position of the wedge. Basically, it's a sort of like a horizontal coordinate, basically like x. Since from the Newtonian formalism, from a Newtonian point of view, since there are no any external forces in the x direction, of course, the corresponding linear momentum is conserved. The total linear momentum in the x direction must be constant, right? Because there are no any external forces. Internal forces, of course, here, and there will be internal forces, right, in the horizontal direction. Right? Normal force, it will have component in the x direction. But again, you remember, internal forces cannot change the total linear momentum of the whole system. We discussed that at the very beginning of this semester. So, and yeah, so you see, mq2 dot, a component, okay, linear momentum of the wedge. It's only in the x direction. And then we have m small q2 dot, right? Again, part of the x component of the linear momentum of m small, and this also x component of the linear momentum of m small. So total linear momentum in the x direction. So which way I wrote it? Conservation of linear momentum in the x direction. Okay, so that's the equation number 1. Let me sort of, probably I will underline it. Right, so and put equation number 1 so that I can use it later. Now, second Lagrange equation for Q2. So it will be partial derivative of L with respect, Q1, we just discussed Q2, d over dt, partial derivative of L with respect to Q1 dot. Okay, now Q1, of course, is not ignorable. It's explicitly present in the last term, right, which basically describe, it's a potential energy of the mass, and it means that there is a external force acting on the mass in the y direction. That's why that linear momentum is not going to be conserved. Linear momentum in the vertical direction is not going to be conserved. Again, I'm just trying to justify it from the Newtonian point of view, Newtonian approach point of view. So dl over dq1. It's only here, only in the last term. Here we have only dots, so it will be, is it the big term? Let me look. Yeah, probably I should start the next line. So it will be mg, q1 will go, so we'll have mg sine alpha equals d over dt, and now partial derivative with respect to q1 dot. This, so it will be mq1 dot, mq1 dot, and this, so it will be, again, 2 will go, we'll have m q2 dot plus m q2 dot and cosine alpha. Right. Okay, so now let's differentiate with respect to time. Again, alpha is a constant, right, and mass is also a constant. Right. M q1 double dot plus q2 double dot cosine of alpha. So now we can use the weapon of mass destruction, and we can cancel all those masses, right? Oh, sometimes it can be called mass murdering, right? So m goes m. Okay, so now let me rewrite without masses. And let me write this first. So q1 double dot plus q2 double dot cosine of alpha equals to g sine alpha. So that's equation number 2. Right. Okay, and now at this point, we can forget that the Lagrangian treated those q's and q dots as linearly independent. Now we need to recall so that q dot, it's a time derivative of q, right? Q1 dot, it's a time derivative of, so now we have these two first order and second order differential equations. So now we just need to solve it for what we want to find. Of course, we can solve it for q1, for q2, but what we want to get eventually, we need to get the travel time of this box when it travels along this inclined plane, which is running away also, right? So in order to find that travel time, we need to find acceleration of q1 double dot, right? Once you know that, and then we will see what can be done to find time. If that acceleration is constant, that will be very simple. If it's not a constant, then yeah, we will suffer more. But basically our starting point is we need to find q1 double dot. So this system of these two equations must be solved for q1 double dot, right? So let me write. So we need q1 double dot, okay, to get TL. So that's the goal. Okay, sort of local goal. Okay, so how can we get q1 double dot? So these equations are obviously coupled, right? And in order to sort of solve it, I would probably do this. We need to get rid of q2 double dot. I will probably just differentiate this one more time with respect to time. to get Q2 double dot. Then I will get Q2 double dot from the first equation and shoved it into the second equation in order to get Q1 double dot. Okay? Does it sound like a plan? Maybe you can go for better, but that's how I did it. So let's do it. So I will do this, differentiate with respect to time, equation number 1. So d over dt out of the equation number 1. Right? Okay, so now, actually I can immediately solve it for Q2 double dot. Right? It's easier, right? So because everything is constant, this will become 0, right? I think I can skip, I can write immediately Q2 double dot, right? Q2 double dot will be equal, this will go to that side with minus m over this, m capital plus m small, right? Then cosine of alpha, and, yeah, Q1 double dot. You know what, let me write this way. I will put cosine over here inside. Cosine of alpha and Q1 double dot. Okay, it looks like this is the, let me check to make sure that I don't make any stupid mistakes. No, it's fine, yeah, because it's simple. And you know what, I will need it closer to the end. Let me frame it with green, right? Not very conspicuous, but so that, but it helps to find. It will help me to find. And so what? Now we just need to plug it into the equation number 2. Now let's put it in the equation number 2. As a result, we will have I'm thinking, should I just solve it? No, let me plug it. All right, so Q1 double dot plus, or not plus, minus, because of this minus. So it will be minus m over m capital plus m small cosine of alpha. And, okay, cosine squared here, cosine, and there cosine. Cosine to the power of 2. And Q1 double dot equals to g sine alpha. Right, so I just plug it into this equation. So Q1, of course, can be factored out. So we're getting acceleration. Awesome. Q1 double dot will be equal this g sine alpha divided by 1 minus this term m cosine squared alpha divided by m capital plus m small. That's the acceleration of the block basically relative to the incline. Right? So you see that in that direction acceleration. And it's constant. Constant. Everything is constant. So let me emphasize, it's a constant. And let me call it A, because it's an ugly looking constant. I don't want to drag it through all my calculations, which I need to do after this. And you know, let me frame it. No, not red. Red is too early. Let me frame it with blue. Right. And emphasize this is. And so now we can easily integrate it. Because again, now, so in order to find travel time, we need to get Q1 as a function of time. And we know Q1 at the final moment of time, it will be equal to the total length of the incline. And so then we can extract the travel time. So let's start integrating it. Q1 equals to AT plus the first constant of integration. Of course, that is 0 because the box was released. So this is 0 since v not equals to 0. Right. Then Q1 now, of course, is a function of time. It will be equal to AT squared over 2 plus the second constant of integration, which is position q1 at the initial moment of time. But you see, we measure q1 from the top, so q1 at the initial moment of time equals 0, right? So this is also 0, since q1 at t equals 0 equals to 0. So as a result, we're getting how q1 changes with time. And now we should be able to find the travel time easily. So now q1 at TL, again, TL it's the total travel time. So at that moment of time, the box will be at the bottom, at the end of the incline, at the end of the wedge. So we know that is L, right? And it is equal to a t sub L squared divided by 2. So we can solve it for t sub L. So now it's basically kinematics, right? So t sub L equals 2 square root of 2L over A. So what about time? Okay, we still have time. Oh, so I will need this. I will need transformation equations. So I need to erase probably the best part. No, damn it, I need that also. Okay, I will erase a Lagrangian. I need the picture so that we can discuss what happens with the system, right? I need transformation equations because I will need them, you will see. And I also need this. Feel like I need to start writing it on walls at some point, right? Okay, so let me separate this. Right. And so let me write explicitly. Do I need that? Okay, you can plug it easily, right? So I'm not going to rewrite the travel time using this constant. You can easily do it by yourself, right? Because now most of the time I'm going to analyze accelerations and so on, right? So you can plug it and rewrite. It's not a big deal. So now let's look. Basically, problem is solved. Problem is solved. Now let's look at some limits, since we still have time. Right. So now let's look at limits. And just when you solve the problem, you want to have some more fun, right? So let's look at the case when, for example, alpha equals pi over 2. Alpha equals to pi over 2. Sort of, it's not a wedge, it's basically like a box, right? And the box, big box, M capital, and of course the small box is on this side. Of course it will go straight down. So are we going to get that? So let's get acceleration. This acceleration, right? Oops. Right, so that A, when alpha equals pi over 2. Cosine of pi over 2, 0. So this is 0, this is 1. So we'll have a g sine alpha. Sounds like Hold it. Pi over 2. Hold it. Sine alpha is pi over 2. So sine pi of pi over 2 is just 1. So g. Of course, we're getting g as it should be. I forgot to apply alpha over here. So will be g, right? So yeah, it's okay. I can put a check mark. The next limit. What if, for example, mass of the wedge goes to infinity? So what does it mean? It means that if you take the nail, right, and nail the wedge to the horizontal surface, so the mass of the wedge becomes infinity, right? So in that case, what will be the acceleration? Q1 double dot A. In that case, m is infinity, so we can forget this. This is too small, so the whole term over here in the denominator is 0. So we'll have only 1. And this, we'll have g sine alpha. It's basically physics 1 problem when we had the box sliding on the inclined plane, and we had acceleration g times sine of angle. So as a result, we're getting, so A equals G sine alpha. Okay, so another check mark point. So, yeah, it works. Now, what if, for example, this wedge is very, very light? So what if mass of that wedge almost goes to 0? M, okay, let me write if. What if M capital goes to 0? Then, again, let's find acceleration. Acceleration will be M goes to 0, so this is 0. It will be M, and this M and M will be cancelled. We'll have 1 minus cosine squared, which is sine squared. Sine squared, sine. So one sine will be cancelled, so we'll have G over sine alpha. G over sine alpha. You remember first when I solved this problem, I kind of looked, oh my God, we're getting acceleration larger than acceleration due to gravity. How come? But then, of course, immediately you realize, what is A? It's a Q1 double dot. It's an acceleration along the incline, And in this case, when mass of the wedge is almost 0, of course, this wedge basically is flying away from the mass, right? So mass is going down, and this wedge is flying away. So we have sort of superposition of two accelerations, right? So we shouldn't be surprised that acceleration is larger than g, because sine is less than 1. So of course, acceleration will be acceleration will be larger than acceleration due to gravity, right? Because it's acceleration along the incline, right? So it makes sense. Also, what's next? I should emphasize, so that is the larger or equal than g. Okay, check mark, makes sense. Then what's next? Okay, we still have a few minutes. Now, you remember when I introduced first transformation equations in a previous class, I told you that we need transformation equations in both directions. Over here, we applied them to move from these Cartesian coordinates to generalized coordinates. Because there, and of course, we will solve the problem using those generalized coordinates, and of course, you will see how those q depends on time. But very often, at the end of the day, you want to know what your system does in these x and y's. So very often, because most of the time you live in a normal grounded coordinate system, in the grounded reference frame, you see what happens to m small, for example, in terms of x, not just q1 or q2. Okay, so let's try to see what happens in this case when m goes to 0. Okay, let me emphasize, let me frame it. So this case, right? What happens with, for example, x small? Acceleration of acceleration. Yeah. Let's talk about acceleration of wedge relative to this inertial reference frame, x small double dot, right? So now, let's look at x double dot. So now, of course, we need to go back to our transformation equations. That's why I didn't want to erase them, because I knew I needed them. I knew I would need them. So I will have q2 double dot, q2 double dot, right? I'm just looking at this equation, right? You see, plus q1 double dot and cosine of alpha. Okay, and now q2 double dot, it's here. That's why I framed it with this green, so it would be easier for me to find. So q2 double dot. So I can plug it here, right? So I will have q1 double dot and here q1 double dot, so it can be factored out. And also cosine alpha and cosine alpha over there. So it will be q1 double dot cosine alpha. And what will be left inside? From this term, it will be just 1. And this is the negative term. So it will be minus m over the total mass. Minus m small divided by the total mass of the system, right? And again, look, what is Q1 double dot in the case when m goes to 0? We just found it's a g over sine alpha. All right, so let me show that I can take this A and plug it into Q1 double dot. So as a result, we're getting this construction. So it will be g divided by tangent of alpha. All right, so sine downstairs, cosine upstairs. Okay, I will use tangent. I like tangent over cotangent. All right, so it will be g divided by tangent, okay, tangent alpha, getting more and more difficult to write. Okay, let me clean this. And that construction, 1 minus m over m capital plus m small. And again, we still haven't applied in the second term m equals to 0, m goes to 0. So when m goes to 0, m capital, so we're getting 0. This is m over m, gives us 1. 1 over 1 minus 1, it's 0, right? So we're getting that x double dot equals to 0, as it should be, because we know if this wedge is massless, then m will just, okay, again, relative to inertial reference frame, it will go straight down. So acceleration in the x direction will be 0. Acceleration in the x direction will be 0, and that's what we got. X double dot equals to 0. So if you do the same for y double dot, can you guess what you're supposed to, what would you get? Will you get? Of course, g, right? So if you apply it properly, right, transformation equations, of course, you should end up with g, right? And probably I will skip that. And if you do the same for x double dot, you will get negative acceleration. X double dot will be negative. It makes sense because, of course, the wedge, in this case, when m goes to 0, of course, it would accelerate that way. Right. Okay, those are just details, right? If you want to have more fun. If we had a few more minutes, I would go into the y double dot and x capital double dot. Okay, enough. Okay, guys, all right. So next class, we're done with this problem. So next class, there will be another problem. There will be a hoop which is spinning around this axis with constant angular velocity. And there will be a mass attached to the hoop, no friction, so that mass will be able to slide back and forth around that hoop. So we will try to write the Lagrangian of that system and solve it. But that system will be more complicated. But that will be Thanksgiving present. Beats like a drum.